It is my pleasure to announce the final lecture of Professor Joy Morris. Professor Morris, please.
So today I'm going to talk about regular representations. So first, let me review a few key points from previous talk. I showed that when we have a vertex transitive graph on a prime number of vertices, it's always a Cayley graph. The automorphism group of a circulant graph on a prime number of vertices is always either doubly transitive or an affine group. And I defined blocks and imprimitivity, that I also defined lexicographic and Reith products. Talked about how imprimitivity allows us to use induction as for an argument. Then showed that explained why the automorphism graph of a circulant group of a circulant graph on a composite number of vertices has to be either doubly transitive or imprimitive, and used that to show an algorithm that determines the circulant graph, the automorphism group of a circulant graph on PQ vertices where P and Q are distinct primes, and it has to be one of these three situations. And stated without giving a full explanation that the automorphism group of a circulant graph on a square-free number of vertices can be found in polynomial time. So, Koenig in 1936, let me see if I can make this go away, asked, given any abstract group G, is there a graph whose automorphism group is isomorphic to G? And the answer came very quickly. Oops. Frucht in 1938 showed that the answer was yes. In fact, there are infinitely many such graphs, but in general, the construction that he came up with required a lot of vertices relative to the size of the group in order to ensure that the automorphism group was exactly what we were looking for. So in 1974, Brian Alspach asked a related question. He asked, given a particular permutation representation of a group G, is there a graph whose automorphism group is isomorphic to G as a permutation group? And although this is the first time the question had been asked exactly this way, some results towards the answer had already been worked on by a variety of researchers, in particular about regular representations. So, but let me, an example of the sort of question, the reason Brian asked this question was, well, the symmetric group on 5 points, for example, has a lot of different representations. For example, whoops, sorry. Sorry, this file is not working properly. I think I'm going to have to open it in a different app. Sorry, because I'm not getting my multiple pages. So. No, it's just not showing up. Okay, so sorry, there's some missing stuff here. So some of the representations of the symmetric group on 5 points include, there's obviously a representation on the 5 points. There's also a regular representation on 120 points. And in fact, every group, and there are many more representations as well, but in fact, every group has a regular representation. So let me define, sorry, I can't write on the screen the way I can't, because I'm not using my iPad. My iPad wasn't working properly this morning for some reason, so I'll just be answering these questions verbally rather than writing. A graph is a graphical regular representation for the group G if its automorphism group, its full automorphism group, is exactly the regular representation for a group G. So a GRR is always a Cayley graph, because we've seen that a Cayley graph always has the regular representation of a group sitting inside its automorphism group. But in fact, a GRR has to have the additional property that it can't have any other automorphisms. So remember that if alpha, we showed that if alpha is an automorphism of the group G that happens to fix the connection set of our Cayley graph setwise, then it actually induces a graph automorphism on the Cayley graph with group G and connection set S. In particular, if our group happens to be abelian and we take any Cayley graph rather than directed graph on this connection set, then the connection set has to be closed under inversion. And therefore, let me call it iota, the automorphism that inverts every element of our group is actually a graph automorphism on the corresponding Cayley graph. So an abelian group can only possibly admit a GRR if the automorphism that inverts every element is actually just the identity automorphism. As an exercise, even though iota is the identity automorphism on the cyclic group of order 2, the cyclic group of order 2 does admit a GRR. It's easy to produce one. In fact, any graph you produce on the cyclic group of order 2 is a GRR on the cyclic group of order 2. But by this argument, I put it as an exercise, but I'm going to answer this question. What other abelian groups could admit a GRR? They're going to be exactly the ones on which iota is the identity automorphism. If inversion is the identity automorphism, that means exactly that the abelian group has characteristic 2. So elementary abelian 2 groups are the only groups of order 2 that could possibly admit GRRs. There's another category, excuse me, of groups that have trouble admitting GRRs, let me say. If we have an abelian group of even order and we choose an involution in that abelian group, then we can define a generalized dicyclic group. And again, sorry, I'm not writing, but the generalized dicyclic group is the group that we get by adding an extra element, say X, whose square is Y, and that inverts every element of the abelian group X. Sorry, of the abelian group A. So this is, for example, the simplest, the sort of smallest example of this where it's interesting is the quaternion group, where we start with a cyclic group of order 4, and we add an extra element whose square is the element of order 2 in that abelian group of order 4, -1, and that inverts every other element in that abelian group. So we can define an automorphism. I'm again calling it iota just for convenience, but it's not inversion this time. In this case, if we fix every element of the abelian subgroup, the abelian index 2 subgroup, and we invert every element of the other coset in this generalized dicyclic group, that is a group automorphism. And yeah, so it's a group automorphism. And this group automorphism implies that no generalized dicyclic group can admit a GRR, because again, this automorphism iota either fixes or inverts every element of the group. Before, our inversion inverted every element of the group. This one fixes some and inverts others, but nonetheless, if I have a connection set S, if it's closed under inversion, it will be fixed setwise by this group automorphism. So this means that no generalized dicyclic group can admit a GRR. And in fact, there are no exceptions in this case because iota does not act as the identity on any generalized dicyclic group. So there are no exceptions in this case. We can't have any generalized dicyclic group that admits a GRR. If we have a disconnected Cayley graph with more than 2 vertices, then unlike when we had exactly 2 vertices, that was a GRR. If we have a disconnected Cayley graph with more than 2 vertices, it will not be a GRR. It's fairly easy to find a non-trivial automorphism of such a Cayley graph that is not part of the right regular representation of the group. A hint is basically it acts as the right regular representation on one connected component, but not on the other connected components. So the general approach, and again, sorry, I'm not going to be able to write down this proof, so I'm going to talk through the ideas. The general approach that has most often been used in finding graphical regular representations of groups is based on a proposition by Nowitz and Watkins that states if we happen to have a connection set that actually generates our group, and the induced subgraph of the Cayley graph on that connection set is, so on the neighbors of the identity vertex, is asymmetric, so has the trivial automorphism group, then our Cayley graph will be a GRR. And the proof of this amounts to observing that if the induced subgraph on the neighbors of the identity is asymmetric, then, well, in order to show that our Cayley graph is a GRR, it suffices to show that any graph automorphism that fixes the identity vertex fixes every vertex in the graph. And if we fix the identity vertex, then we certainly fix the neighbors of the identity vertex, which is the set S, and therefore we fix that set-wise at least, and therefore we fix the induced subgraph on that connection set. And if that induced subgraph is asymmetric, then we must actually fix those vertices pointwise. So fixing the identity vertex forces us to fix every neighbor of the identity, and this argument can be used inductively because our graph is connected to show that, in fact, every vertex of the graph has to be fixed. This approach actually allowed Imrich back in 1970 to construct graphical regular representations for elementary abelian 2 groups. As I said, even though these are abelian groups, they may possibly have GRRs, and in fact, most of them do. I'm just going to focus on the elementary abelian group of rank 6, but Imrich came up with a construction that works for any elementary abelian group of rank at least 6. He claimed in the same paper that his construction worked for rank 5. Various people noticed that that was a mistake and fixed it, came up with a different one that works for rank 5. So there are GRRs for elementary abelian groups of rank at least 5. And the idea that I'm about to show here works as long as the rank is at least 6. It needs to be tweaked a little bit for rank 5 exactly. But there are not GRRs for the elementary abelian 2 groups of ranks 2, 3, or 4. So 1, there's a GRR. Rank 1, there's a GRR. Rank 5 or more, there's a GRR. So suppose our elementary abelian 2 group of rank 6 is generated by these 6 involutions, A1 up to A6.
Excuse me.
Yes.
We see one of your old slides, a question by Alspach, 1974, and nothing changes.
Okay, I'm sorry. Yeah, it says my screen sharing is paused. I don't know why that is. Let me stop the sharing and restart it. Now, are you seeing the slide about the GRR? Okay.
Maybe it might be reasonable to show your previous slides after the question by Alspach.
So,
and maybe
question by Alspach. I talked about the representations for the symmetric group on 5 points. This is a graph, just my definitions of a graphical regular representation and so on. And then I had a slide about automorphisms that fix the connection set-wise, inducing graph automorphisms. And the cyclic group of order 2 admitting a GRR. And then I defined generalized dicyclic groups and discussed that there is this automorphism of them that
also for some reason we don't see a part of the lower part of the definition. We see just generalized.
That was, I intended to write that in, and unfortunately I'm not able to use my iPad, so I can't write this in. Okay. So I went over it verbally. And then I had these exercises. I had this proposition by Nowitz and Watkins, which I talked through the proof of. And now I was on to this GRR for the elementary abelian group of rank 6. So we have a cyclic group of ranks, sorry, an elementary abelian group of rank 6. It has these 6 generators, A1 up to A6. And for the connection set, we take each of these generators, A1 up to A6. We also throw in the product of each pair of consecutive generators, A1, A2, A2, A3, A3, A4, A4, A5, and A5, A6, but not A6, A1. And then we throw in 2 more things, A1, A2, A4, A5, and A1, A2, A5, A6. And with this connection set, the induced subgraph on the set S, which is the neighbors of the identity, is in fact asymmetric. And I'm going to demonstrate that by, I've drawn here the induced subgraph on the neighbors of the, on the set S, the neighbors of the identity. And the first thing to observe is there is only one vertex of valency 6 in this induced subgraph, A1, A2. So if we fix the identity, we have to fix the vertex A1, A2. And then this vertex A2 is the only neighbor of A1, A2 that both has valency 4 and has a unique path of length 2 to the other neighbors of valency 4, which are A5, A6, and A4, A5 of A1, A2. A4, A5, and A5, A6 have this second path between them of length 2 going through A5. So A2 also has to be fixed pointwise, sorry. And then A3 is the only neighbor of A2 that has valency 4, and so it also has to be fixed pointwise. Then A4 is the only neighbor of A3 that has valency 4 that we haven't already said is fixed, so it also has to be fixed. And similarly, A5 has to be fixed. And now A5, A6 is the only neighbor of A5 that has valency 4, and we haven't yet said has to be fixed, so it has to be fixed. And then we have some vertices that are unique mutual neighbors of pairs of vertices that we've decided are already fixed. A1, A6, and A1, A2, A5, A6 all fall into that category. So they all have to be fixed, and now we only have one vertex left, so it has to be fixed as well. So using that lemma by Nowitz and Watkins, we can show that Immerich's construction does produce a GRR for elementary abelian groups of rank 6 and more generally higher ranks if we generalize his construction. In 1981, Godsell was able to use results by a variety of previous researchers to complete the proof and show that with the exception of the abelian groups on which inversion acts non-trivially, so ones that are not elementary abelian, and generalized dicyclic groups, so those can't possibly admit GRRs, but with those exceptions, there are only 13 small groups of order at most 32 that don't admit a GRR. So we can similarly define digraphical regular representations, short form DRRs, and a directed graph is a digraphical regular representation for a group if it's a digraph and its full automorphism group is exactly the regular representation of the group G. So again, a DRR will always be a Cayley digraph on the group G. But we've already seen, again, that a Cayley graph on the group G always contains the G as the regular representation of G in its automorphism group. So again, we're looking exactly for Cayley graphs that have no extra automorphisms in their automorphism group. If a group admits a GRR, then it also admits a DRR, because a graph is a special kind of digraph that has digons between any pair of vertices. So any GRR is a DRR, but the converse is not true. We can have DRRs even if there aren't GRRs. So Godsel's result told us already that there aren't very many possibilities for families of graphs where we might not have DRRs. But in fact, Babai, slightly before Godsel, was able to show that with the exception of the quaternion group of order 8 and the elementary abelian groups of orders 4, 8, 9, and 16, every group admits a DRR. So there are only 5 exceptional groups. In this case, there aren't any infinite families as there were for GRRs, and there are only 5 groups that don't admit DRRs. So it's a reasonable question. Oh, and part of the reason it was much easier for Babai to prove this result about DRRs than for Godsel is he had a lot of flexibility to use. He could use arcs and edges in his graphs, and therefore it was much easier to come up with graphs where the neighborhood of the identity was asymmetric. But let's talk about some other structures that people have studied similar problems on. So a tournament is an orientation of a complete graph. And in some cases, of course, we can make a tournament a Cayley graph. An oriented graph is an orientation of a graph. And so this is a special kind of directed graph where we don't have any edges between vertices. We only have any connection between 2 vertices goes in only one direction. And another, a Frobenius representation of a group is different from the regular representation. It's a representation only some groups have Frobenius representations, and these are representations in which only the identity element fixes more than one point. So for groups that have Frobenius representations, it's potentially interesting to study whether or not the groups have graphical Frobenius representations. So researchers have studied tournament regular representations and determined that, well, every group of odd order has a tournament regular representation, if I recall correctly. Oriented regular representations, this was work by Pablo Espiga and myself, and we were able to show, again, that there are finitely many exceptions and one infinite family of groups that cannot have oriented regular representations. Basically, the infinite family is groups that require an involution in their generating set. If a group has to have an involution in its generating set, then in order to get a connected Cayley graph on a Cayley digraph on that group, we have to have an involution in the generating set, and therefore we have to have an edge rather than a directed edge in the corresponding graph. So we can't possibly have an oriented regular representation for a group if it requires an involution in its generating set, again, unless the group is the cyclic group of order 2. But other than that infinite class, it turns out that there are, again, only a finite number of exceptional groups that do not admit ORRs. I believe there are 32 of them. Graphical Frobenius representations were studied by a PhD student of Mark Watkins, who completed his PhD but died without publishing his work. And Mark Watkins did go on to work on publishing some of those results later on behalf of that student. And bipartite graphical regular representations are another very interesting class that has been studied. The reason they're interesting is because in this situation, if the graph is bipartite, we can't make any reasonable use of that result by that lemma by Nowitz and Watkins, which all of these other results really relied on quite heavily, that if we look at the neighbors of the identity and the induced subgraph on them happens to be an asymmetric graph or digraph, then we have a GRR or a DRR or whatever it might be. If we want to, if we have a bipartite graph, then the induced subgraph on the neighbors of the identity will be empty. So it's certainly not going to be asymmetric. And of course, we can look at the square of the graph and get some edges potentially, and maybe get some, maybe use that to get a similar sort of idea. But in general, actually, people have used quite different techniques to construct bipartite GRRs. And I believe there are not, to my knowledge, there aren't complete results about bipartite GRRs at this point. Only partial results on families. So the general message of this, what I've been talking about today, is that symmetry is abnormal. And there is, of course, a famous result by Erdős and Rényi back from 1963, showing that almost every digraph is asymmetric asymptotically. And similar results have also been proven in this context of graphical and digraphical regular representations. So myself and Pablo Spiga in 2021 managed to prove that if we take an arbitrary group of order R, as long as R is sufficiently large, then we could actually quantify, or bound rather, the number of subsets for which the Cayley graph is not a digraphical regular representation. We could bound it as 2 to the R minus some function. B is an absolute constant. And this is a relatively small proportion of the total number of Cayley digraphs, because we can choose any connection set. We can choose any subset of R for our connection set S. So there are 2 to the R subsets in total. And so using this result, we're able to show that this is, as I say, a vanishing fraction of 2 to the R, the number of labeled Cayley digraphs on R. And in fact, we were able to prove that up to isomorphism, so this shows that almost every Cayley digraph is a DRR. And in fact, we are also able to show that up to isomorphism. Directly, this only shows that every labeled Cayley digraph is a DRR, but we were also able to show that up to isomorphism, almost every Cayley digraph is a DRR. And more recently, Shasha Zheng, in her PhD thesis, together with her supervisor Binju Xia, showed a corresponding result for Cayley graphs. So almost all labeled Cayley graphs are GRRs, as long as they're on a group that admits a GRR at all. And also up to isomorphism, almost every Cayley graph is a GRR. But these are the only two categories for which asymptotic results have been done. And and the technique, while they use similar techniques to ours, it required some careful work and a few tricks that we didn't think of to get the result for Cayley graphs rather than just Cayley digraphs. That's the end of what I wanted to cover today. Again, apologies for the late start and the fact that my iPad wasn't working, and so I wasn't able to write things out. But that's the end of today's talk. Thank you.
Okay, thank you for this nice explanation. Any comments, questions? Okay, so let us thank the speaker, and the mini course is over. Thank you.
Thank you.
Okay, bye.
Bye.